Okay, now for the second part of question 4. Now we're looking about hydrolysis of a protein to release those amino acids. Conditions for hydrolysis, the standard conditions are that you reflux with 6 molar aqueous HCl. Probably isn't vital to remember the 6 molar, but aqueous HCl. It must be aqueous because it's hydrolysis reaction. And then it says, okay, you can separate the amino acids using gas-liquid chromatography, and you've got to explain why that should separate different amino acids from each other. So just quickly, to remind you how that works, you don't need this diagram obviously in your answer, but the idea of gas-liquid chromatography is you inject your sample, you do this whole thing in an oven so that everything turns into a vapour, and the vaporized sample is carried through this long column on a stream of gas until it reaches the detector there. And what you measure is the retention time, which is the time taken between the sample going in here and the component being detected there. And what slows it down is that the column is lined by this layer, which is shown in red there, which is a layer of liquid lining the column. And the idea is that if the sample tends to dissolve in the liquid as it goes through the column, that will slow its progress down. So the two factors that you need to talk about are, first of all, that the more soluble the amino acid is in the liquid that lines the column, the longer its retention time will be. Okay, the more soluble it is, the more likely it is to get slowed down by lingering in the liquid phase there. So more soluble, longer retention time. The other is that the more volatile the amino acid is, the easier it will find it to escape from the liquid again and carry on its way. So the more volatile the amino acid, the shorter the retention time will tend to be. So make sure you talked about both of those things. Solubility in the stationary phase, which remember is the proper term for the liquid lining the column, and volatility. Okay, the next thing it asks you about is stereoisomerism. So what you need to explain is that because the amino acid has a chiral center, this carbon here, 4 different groups around it means it's a chiral center, and that means it can exist as a pair of optical isomers. It's always a good idea to explain what that means, non-superimposable mirror images. So it exists as a pair of optical isomers which are non-superimposable mirror images, and you have to draw the picture. When you do this, make sure you do 3-dimensional pictures like that. Show the tetrahedron, practice drawing them, make sure you don't get a horrible squashed tetrahedron, that's the approved way to draw them. And you draw the other one as a mirror image of that. You must draw them in the mirror image orientation, otherwise the examiner won't understand what you're trying to show. So you draw it as if there was an imaginary mirror running down there. Okay, and those are the 2 optical isomers. And then it asks you whether you would expect to find this second isomer as well as amino acid Q in your protein hydrolysate, and the answer is no, because remember that proteins in nature are formed only from one optical isomer of each amino acid, so you would generally expect in the protein hydrolysate to get one and not the other. Okay, that's it for question 4. One more question to go.